This is a
It's 2 minutes, sir. So could you give us 2 minutes, sir? A couple of people are still joining, so they're having some problems because
okay,
they're
okay, okay. Okay, so let's start. This is a course on signals and systems. You might already have some of the classes by Professor Nandi. I will take some of the classes and Professor Nandi will take the others. So today we are going to start with what is signal and what is a system. What is the relationship between.
Sir, your voice is cracking.
Now?
So you can turn off your video. That way, bandwidth will be consumed lesser. Then your voice will be clear.
Is it okay now?
Yes, sir. Now
yes,
it's
sir.
okay.
Okay. Okay. I'll be talking about signals today. So what is a signal? A signal is a function of one or more independent variables that carries some information to represent a physical phenomenon. So for example, you might have a damped system that might have a signal like a to the power minus a t. So there are some types of signals like a continuous time signal, also called the analog signal, is defined along a continuum of time. So a signal carries some information to represent a physical phenomena. A discrete time signal is a defined in discrete times, like xn equal to a to the power n. So that n equal to 0 will have some value, n equal to 1 will have some value. Just contrast this with the previous figure. In the previous figure, it was continuous with time. In this figure, it is just discrete. That means it has values only for n equal to 0, 1, 2, and so on. But in here, you have values for all values greater than t greater than equal to 0. Okay. Now, elementary signals, most elementary form of signals you will find in sinusoidal signals and exponential signals. Sinusoidal signals are expressed as a sine 2 pi by t0 t in the cyclic form, a sine 2 pi f0 t, or a f0 is the frequency, t0 is the period. So that is equivalent to a sine 2 pi by t0 into t. Now it has a frequency, it has a radiant frequency form a sine omega 0 t, where omega 0 equal to 2 pi f0 equal to 2 pi by t0. And t0 is called the time period of the sinusoidal wave. So you have one sinusoidal signal like a sine 2 pi f0 t or a sine omega 0 t. This is a sinusoidal signal. Similarly, you have an exponential signal, that is a e to the power minus at. So sinusoidal signals have, for example, xt equal to a sine 2 pi omega 0 t plus theta. This is a sinusoidal signal. Now, this signal is different from the previous signal a sine omega 0 t in that it has a plus theta. This is called a phase of the sinusoidal wave. So when t equal to 0, this will represent at t equal to 0 at which point the sinusoidal signal starts from. This is called a phase. Similarly, real exponential and complex exponential signals are also found. Xt equal to a to the power at is real exponential, and xt equal to a to the power j omega 0 t equal to a cos omega 0 t plus j sin omega 0 t is a complex exponential. Here theta is called the sinusoidal, theta is called the phase of the sinusoidal wave, a is called the amplitude, f0 is called the fundamental cyclic frequency, and omega 0 is the radiant frequency of the signal. So sinusoidal signal, you have already done this in your class 12 course, right? Yes? Hello.
Yes, sir. Yes, sir.
In complex analysis, you have done some part of it, right? Complex numbers. Okay. Now next comes the unit step function. Unit step function is defined as ut, which is equal to 1 if t is greater than 0. This is equal to half if t equal to 0 and equal to 0 if t is less than 0. So it has a precise graph like when t equal to t is less than 0, it is all zeros. When t is greater than 0, it is 1. And when t equal to 0, it is half. But this commonly used graph is like this. Commonly used graph is like this. It has a step function like a staircase function where t equal to 0 means all zeros, and then a steep rise at t equal to 0. T is less than 0 means all zeros, and there is a steep rise in t equal to 0 and else at 1 for t greater than 0. So this is called the unit step function. The signum function or the sine function is defined as sine t equal to 1 if t is greater than 0, sine t equal to 0 if t is equal to 0, and sine t equal to minus 1 is t is less than 0. You can see this is 2 of ut minus 1. Ut is this function, and your sine signum function is this. So you can see that signum function is 2 ut minus 1. So it has a graph like this. When t equal to 0, the value of the signum function is 0. When when t is less than 0, the value of the function is minus 1. So it is minus 1 signal is given, minus 1 value is given there. And when t is greater than 0, it is 1. This is the precise graph. But commonly used graph is this, where you have a steep continuous value from minus 1 to plus 1 at t equal to 0. So it is closely related to unit step function by 2 ut minus 1. Now comes the unit ramp function. The ramp function is defined as ramp t equal to t if t is greater than 0 and equal to 0 if t is less than equal to 0. So the function is like a triangle, like a slope of a head. Okay, now this is equal to unit functions integral between minus infinity to plus t, which is equal to t into ut. Is that correct? The ramp function is integration of minus infinity to plus t, u lambda d lambda. Is that correct? Yes.
Yes, sir.
How? How? Just integrate u lambda d lambda and you will see that this is TUT. So for u lambda minus infinity to 0, the value is what? Minus infinity to 0, the value is 0. Okay, so that is crossed out. Then there is a half value at 0, which is also discarded because it is a 1 point value. And then you have from 0 to t. From 0 to t, the value is 1. So the value will be t into ut, right? So the unit ramp function is the integral of unit step function. It is called unit ramp function because for positive slope, its slope is 1 amplitude unit per time. Clear? So this is the unit ramp function. So we have seen sinusoidal function, we have seen exponential function, we have seen unit step function, and we have seen signum function, and we have seen unit ramp function. A rectangular pulse or gate function. Rectangular pulse function is given by this delta A t equal to 1 by A if mod t is less than half. So within half with the plus side and minus side, the value is 1 by A. It is 0 otherwise. And at 0, the value is undefined. At 0, the value is undefined. So it is plotted like a rectangle, like a rectangular pulse, as you can see in this picture. And the value at t equal to t less than minus a by 2 is t greater than a minus a by 2 is 1 by a, and this less than a by 2, the value is minus 1 by a. And so this is a rectangular pulse or gate function. Questions? Yes? Okay. Now comes the unit impulse function. As A approaches 0, gt approaches a unit step and g dash t approaches a unit pulse. Step and g dash t approaches a unit impulse. Functions that approach unit step and unit impulse. So gt as A approaches 0, gt approaches a unit pulse and g dash t also approaches a unit pulse. So unit impulse function is the derivative of unit step function or unit step signal of unit impulse function. So impulse means just a single line, just like this. This is an impulse. So impulse is just like a single line from at t equal to 0 or t equal to 1, whatever it is. And the value is given by, generally for unit impulse function it is 1. Otherwise the value is given by 5 delta t. Here the value of delta t is 1 at t equal to 0 and all other values are 0. T greater than equal to or less than greater than 0 or less than 0. All other values are zeros. And for impulse at 5, the value will be 5 delta t. The value at t equal to 0 will be 5. And for unit file for at t equal to 0, a shift impulse function, shift will go later on, shift will see later on. So unit shift function, unit impulse function is given by 5 delta t minus 1. Properties of impulse function, the sampling property. GT is the ramp function. Ramp function into delta t minus t0 dt equal to gt t0. So if you sample, that means if you sample gt over an impulse function, then you get simply g of t0, nothing else. It's obvious because at t equal to 0 only the value is 1, or other places the value will be 0. So the sampling property gives that gt delta t minus 1 dt is equal to gt t0. The scaling property delta a of t minus t0 equal to 1 by a mod a delta t minus t0. And the replication property is that gt convolution delta t, you will see at this symbol later on what is this symbol, but gt convolution delta t equal to gt, we will see what is this symbol. So three properties are there for impulse function. The sampling property says that integration minus infinity to plus infinity gt delta t minus t0 dt equal to gt. The scaling property tells that delta a t minus t0 equal to 1 by a. One by mod a delta t minus t0. The replication property is gt convolution delta t is equal to gt. Now, unit impulse train. The unit impulse train is the sum of infinitely uniformly spaced impulses and is given by delta tt equal to n equal to minus infinity to plus infinity delta t minus nt, where t is the period and n is an integer. That means it will have at t equal to 0 1 a value of 1, at t equal to t a value of 1, t equal to 2t a value of 1, t equal to minus t a value of 1, t equal to minus 2t the value of 1, etc. etc. Okay. So this is unit impulse train. Unit rectangle function. Unit rectangle, if the rectangle is of size, the unit rectangle or gate signal can be represented as a combination of two shifted unit step signals as follows. Unit step, you remember unit step function. Unit step function was was like staircase step, where t equal to 0 means the value is half, t greater than 0 means the value is 1, and t less than 0 means the value is 0. So it can be represented the unit rectangle function can be represented as ut plus a minus ut minus a. So a shift of minus a and plus a is given there, and their subtraction is taken as the unit rectangle. The unit triangle function, the triangular pulse whose height and area are both 1, but its base width is not, is called the unit triangular function. The unit triangle is related to the unit rectangle through an operation called convolution. We will see what is convolution. So if the width of the triangle, if the height and area, if the height and area of the triangle is 1, of a triangular function is 1, then it is called a unit triangular function. Sinc function, this is important. Sinc t is equal to sine pi t by pi t. So the look of the function is like this. It is like sinusoidal damping function, you can say, but it is actually damping in both ways, in the negative direction and in the positive direction. Okay. So do you have any questions till this part?
So what is the significance of the sinc function, sir?
Sinc function is like a damping function. As you will see in the damping function, what happens is, if you, let's say you have a simple harmonic motion, let's say you have a ideal fork. Now if you damp it with a load, what will happen is the period will change. The period will the time period will be less and less every time, and then ultimately it will become 1. It will become 0. So that is actually represented by the sinc function. It is kind of like a damping function. It is not exactly the damping function, but it is kind of like a damping function. Okay. Any other questions? Anybody? So what we have seen is a lot of functions we have seen. Though it will not be difficult for you to understand what are the functions because you have already done this in your class 12 course. But the functions are very important. Now the functions are like unit triangle function, unit rectangle function, unit impulse function. Did you understand this? Ut plus a minus ut minus a rectangle t equal to? Did you understand this?
Yes, sir.
How? Explain why this is true.
Sir, because according to the definition of ut, if it's greater than 0, like just the definition of ut, if it's greater than 0, it's 1, and then it's 0. So if we consider that t is getting shifted by a, so uh, that that is for the positive side of t, and it's getting shifted by minus a is the negative side of t. So we are just shifting the graph that way.
Right. Okay. Now discrete time signals. As we have seen that there are continuous time signals and discrete time signals. Discrete time signal means you have values of the signals at discrete times like n equal to 0, n equal t equal to 0, t equal to 1, not any continuous values. Now sampling is the acquisition of values of a continuous time signal at discrete points in time. So what you can do, for example, you cannot hold a continuous time signal, right? What you can do is you can sample it at t equal to 0, at t equal to 1, at t equal to 2, etc. etc. So if xt is a continuous time signal, then xn, x third bracket n is a discrete time signal, and x third bracket n equal to xn ts, so t is the time between the samples. So ts is the frequency of the sampling. Ts is the time period of the sampling. Okay. So that means you have at n equal to 1, you have taken a sample, what is the value of xt at that moment, and that is the value of x third bracket n, third bracket 1, and so on and so forth. So discrete time sinusoidal system, discrete time signals can be defined in a manner analogous to continuous time counterpart. Like discrete time sinusoidal system is, instead of you giving f omega 0 or f or 2 pi by t0, you give n by n0. That is a discrete type sinusoidal system. Or you give a sine 2 pi f0 n plus theta, where theta is the phase and no frequency is f0. Discrete time exponential signal is given by xn equal to a to the power n, where in these two pictures, in these two equations, n is the discrete time, a is the amplitude, theta is the phase shifting of the in radians, n0 equal to discrete period of the wave, and 1 by n0 equal to f0 is the discrete frequency, is equal to sigma 0 by 2 pi is equal to this discrete frequency. So for example, you can see the sinusoidal discrete time signals. All of these are sinusoidal, as you can see, but the values change. The signal samples are taken at different points. So this point is one value, and then maybe it is coming like a small period, but the period of the discrete time signal is more. All of these are sinusoidal waves. So can you tell which of the four discrete time sinusoidal system in the corresponding continuous time sinusoidal system which has the most maximum period? Yes.
So could you repeat the question once more, sir?
I am telling these are all continuous time signals, right? And sampled at different times, right? Am I right?
Yes, sir.
Now I am telling all of these are sinusoidal waves. So which of the sinusoidal wave has the longest period of these four?
Sir, the last one.
Right. The last one has the longest period. And the smallest period?
Sir, the first one, if I'm not wrong.
Yes, first one. Right. Okay, so that way, so what you are doing basically, you have a continuous time signal and you are sampling it at different moments in equal space time. That is the equal period of equal space time. And what you find is the value of the discrete time sinusoidal signal. Note that the period of the discrete time sinusoidal signal and the value of the continuous time sinusoidal signal, the periods are different. Is that correct? Is the periods different? Yes. The periods of sinusoidal continuous and sinusoidal discrete time are different. Is that correct?
No, sir, they're the same because it's just the crest and trough combined.
Right. Yes, that's right. Now, discrete time unit step function or unit sequence functions is u third bracket n equal to 1 if n is greater than equal to 0 and 0 if n is less than 0. So it will look like this, like for n equal to -1, -2, -3, the value will be 0 and equal to 0, 1, 2, 3, the value. This is discrete time unit step function. Similarly, ramp function you can say ramp of n equal to, this is also you can see this is simply a continuous time ramp functions sampling. Am I right? Yes. Yes.
Yes, sir.
It is a sampling of the continuous time damp function at different points where it is n equal to where the period is 1. Am I right? Unit. Right?
Yes, sir.
Right. Okay, discrete time unit impulse function is similarly defined. The value n equal to 0, the value is 1, and n is not equal to 0, the value is 0. So delta n equal to delta n for any non-zero finite integer. Delta n equal to delta an, is that correct? Yes?
Yes.
Because you can see by definition that n equal to 0, the value is 1. So that means n equal to 0, the value is 1. N equal to 0 implies n equal to 0. Right? Okay. The discrete time unit impulse is a function in the ordinary sense in contrast with the continuous time unit impulse. It has sampling frequency, it has no scaling property. Scaling property was there in the unit pulse continuous signal, right? Remember the scaling property of the unit
Yes, sir.
pulse system? What was the definition?
Sir, is the integration of minus infinity to plus infinity gt into delta t minus t naught dt equal to gt naught.
No, it is the I am telling the scaling property. Sampling frequency is okay. Sampling property is both has the both the continuous time and the discrete time both has the sampling frequency. What about the scaling property? Now the scaling property, what is the scaling property for the continuous time pulse, unit pulse? Yes,
So that I don't remember, sir, actually.
that
Sir,
is equal.
the
Yes,
delta
yes. Delta A T
T
equal
minus
to
T naught.
T minus T naught is equal to 1 by mod A delta T minus T naught.
right. So that is true for continuous time, but that is not true for your discrete time, right? Because we have seen that delta n equal to delta an in this case. Operations of signals, sometimes a given mathematical function can completely describe a signal. Different operations are required for different purposes of arbitrary signals. The operations on signals can be time shifting, time scaling, time inversion, or time folding. We'll see from this point next class, but just to review some of the points today. So what we have seen is a continuous time signal. I have seen first of all that a signal is nothing but a electrical signal that carries some information to represent a physical phenomena. We have seen there can be continuous time signal or discrete time signal. Elementary signals are sinusoidal or exponential signals. Sinusoidal or sinusoidal signals are represented by a sine 2 pi f0 t plus theta, where f0 is the frequency and theta is the phase. Exponential signals are represented as a to the power at. Unit step function we have seen, signum function we have seen, unit ramp function we have seen, rectangular pulse or gate function we have seen, unit impulse function we have seen when both a tends to 0 in case of the tram function or in case of the rectangle function, then what we get is the unit impulse function. Then we have seen the sampling property, scaling replication property of the continuous time impulse function. That is actually true for continuous time impulse function, but all these properties are not true for discrete time impulse functions. Then we have seen unit impulse train, unit rectangle function, unit triangle function, sinc function, discrete time signals. We have seen that it is nothing but a sampling of continuous signal at different times, and what it is for a period TS we sample a continuous signal for n equal to 1, 2 and so on. Then we have seen discrete time sinusoidal, discrete time exponential signals, and